William Pavlov.
Hey guys, this is Mrs. Hartman, and we are doing section 6.6, factoring polynomials. Now, we factored quadratics already, or x squared functions, and this is really not too different, except for we might see an x cubed or an x to the fourth, but a lot of the principles are still the same. Our life application for this unit is that you, the student, will see that representing information in multiple forms should maintain the integrity of the information. Speaking God's written word should be matched with actions. When people look at what we say and look at what we do, they should see that there is a correlation, that they match. When we graph this data, we want to make sure that our data, our numbers, represents what we're actually graphing. Our lesson objective for today is that you, the student, will find remainders and evaluate functions using the remainder theorem, and factor polynomials using the rational root theorem, factor theorem, and synthetic division. So we're doing two basic things today. We are finding remainders and evaluating functions, and we're going to do that using the remainder theorem, which I think is a really cool little shortcut or theorem. And then we're also going to factor polynomials using things that we've already used before. The rational root theorem is new, but factoring and synthetic division, those are things that you've done prior to this lesson. Let's warm up by factoring x squared minus 3x plus 2. Now, we've been using this little shortcut tool to help us remember that we are looking for two things that when multiplied equal AC and add up to B. And our 1 times positive 2 is a positive 2, and our B term is a negative 3. Now, because our coefficient is 1, we can just go ahead and split right into 2. We don't even need to do the grouping, and put our two factors here. And the two factors that when multiplied equal positive 2, but when added equal negative 3 are negative 2 and negative 1. So we've got x minus 1 and x minus 2. To find the zeros of this function, x squared minus 3x plus 2, we would then take each of our factors and we would set them equal to 0. So factoring finds zeros, and zeros is where our graph is going to cross that x-axis. Don't forget that. We have some general forms of equations that we've already seen. First, we have our linear function. A linear function is just when x is raised to the first power, and this was our y equals mx plus b, our slope-intercept form of this function. Our quadratic function, which said that ax squared plus bx plus c, and that's what gave us our parabolas. Linear functions gave us straight lines, quadratics gave us parabolas. Those are the two forms that we've seen so far in our functions. A function that can be written in this form, and I'm not going to try and read this. I'll explain it to you in layman's terms in just a second, where n is a non-negative integer, so our exponent cannot be a negative integer, and the coefficients are real numbers, is called a polynomial function. Basically, if we have a list of terms and our x is being raised to an exponent that's not negative, and we've got coefficients that are also real numbers, that's a polynomial. So x plus 3, or y equals x plus 3, that's a polynomial. Y equals x squared plus x plus 3, and that's a polynomial. Now, these were specific types of polynomials, linear and quadratics. Now, we're going to get into things like x cubed plus x squared plus x plus 3. And we've already seen these longer polynomials when we were doing long division and synthetic division, so these shouldn't be too scary. Let's start off by looking at our remainder theorem. The remainder theorem is a pretty cool theorem, in my opinion, and we'll show you how it works. So the remainder theorem states that if a polynomial, which we're going to label p of x, is divided by a binomial, like x minus a, the remainder is the same thing as p of a. Now, that may not make a whole lot of sense until we put some numbers with it, so let's explain here. Let's find the remainder when this is our polynomial, and it's divided by this binomial. Well, we could use long division, we could use synthetic division, or we can just take our number here and plug and chug and see what the remainder is. So we're going to evaluate the function with this number. We'll plug in our 1 and simplify using the order of operations. And we find that when we plug in our 1 and we evaluate the function, p of 1 equals 3. If we were to divide using long-run synthetic division, this whole thing, we would also get 3 as our remainder. I'm going to prove it to you really quickly. All right, we're going to divide by 1. And using synthetic division, we have x to the 4th, x cubed, x squared, x, and our constant term. And we're going to bring down, multiply, 1 times 1 is 1, and add. Negative 6 plus 1 is negative 5. Multiply, 1 times negative 5 is negative 5, and add negative 6. 1 times negative 6 is negative 6. 2 plus negative 6 is negative 4. 1 times negative 4 is negative 4. And 7 minus 4 is 3. So you can see our remainder is 3. The reason that I think that this is such a cool trick is if you're given this function and you're asked to plug in chug, you don't have to plug in chug. You can use synthetic division to find what that function is at that particular value. I'll try to show this to you in class because I don't have enough room in my space to explain that right here. All right, but basically when we divide by a binomial and we get the remainder of 3, like you see in synthetic division, another way that we can find the remainder is just to plug that number in. And when we evaluate the function, we also get the remainder. A second theorem you need to be aware of is called the factor theorem. A binomial, x minus a, is a factor of a polynomial, p of x, if and only if p of a equals 0. Now, we've already said that before. When we did long division and when we did synthetic division, when we divided by those binomials, we said that if we got a remainder of 0, it must be a factor. Okay? Because our factors are zeros. So if the remainder is 0, it's a factor. I'm trying to go on to the next slide here. Let's determine whether x plus 2 is a factor of this polynomial. Okay, we're going to do that. We could long divide, we could use synthetic division, or we could evaluate it at the negative 2. So we're going to evaluate it for negative 2, which is plug and chug using order of operations. If you tend to make mistakes with the order of operations, a better path for you might be synthetic division. And I'll show you what that looks like in just a moment. We find out that when we plug in that negative 2, we do get a 0. So x plus 2 must be a factor. If we're going to do synthetic division, we've got our 4th term, our 3rd term, our 2nd term, our linear term, our constant, and we are going to divide it by, I don't know why I put the box there, we're going to divide it by negative 2. Bring down, 1 times negative 2 is negative 2, add, 0 times negative 2 is 0, add, negative 2 times 2 is negative 4, add, and negative 2 times negative 1 is 2, add. All right, we got a 0 there. So if you make a lot of mistakes when you plug and chug and orders of operation just messes you up, synthetic division might be the best way for you to go to determine whether something is a factor. X plus 2 is a factor of this polynomial. The rational root theorem generates a list of all possible rational roots of a polynomial function with integral coefficients. What that means is this. Sometimes we're asked to find the roots of a function and they don't give us any starting point. In the remainder theorem and the factor theorem, they gave us a place to start to see if those were roots, if they were zeros. But sometimes they don't give us a place to start. In that case, when we're looking at a polynomial function, it has integral coefficients, and c over d is a rational zero or root in simplest form. Now, what does that mean? That means then c is a factor of the constant term, and d is a factor of the leading coefficient. That gives us all of our possible roots. Let's take a look at what I mean. Here's our c term, our constant, and here's our leading coefficient, which is 1. In order to find all the possible roots, we're going to list the factors of c. So the factors of negative 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And the factors of d are just plus or minus 1. So all of our possible roots are plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, and plus or minus 6 over 1. So these are our 4 possible rational roots listed out there for you. So those are our possible zeros. So when we're trying to test what our zeros are, we really just have to do this and then pick one until we find one that works. So if we plug in p of 1, for example, we get a remainder of -3. So 1 is not a factor. When we plug in -1, we get a remainder of -15. So -1 is not a factor. When we plug in 2, we get a 0. So 2 is a factor. Sorry, I had to pause and resume here, so there might have been a little glitch there. We can also prove that p or 2 is a 0 because we can use synthetic division. And when we use synthetic division, we bring down, we multiply, we add, multiply, add, multiply, add. We end up with, again, a 0 remainder. So therefore, x minus 2 is a factor. 2 is a factor, so x minus 2 is how we would write that. And then what's left is our depressed polynomial. This becomes our constant term, our x term, our x squared term, and then if we had more this way, x cubed, x to the 4th, etc. So our depressed polynomial is x squared minus x plus 3. The quotient, that x2 minus x plus 3, of a polynomial divided by one of its binomial factors is called the depressed polynomial. I've been using that term from the beginning, so that shouldn't be anything new. Depressed just meaning reduced, in a reduced form, not depressed as